every node in the system. What we do is that we just identify the k nodes with the lowest trust value as a compromised node. Okay. So we're going to see that by taking advantage of the special property of sensor networks, can we do better than treating it as a general decentralized P2P system? Okay. So this is shows the deployment density's impact on the performance. Okay. On the left we have detection rate, and on the right we have the false positive rate. Okay. And so we vary the number of nodes in the system from 50 to 250. Okay. So the first observation here is that the eigenrep is not going to achieve the same detection rate as general plus MM. Okay. So that means if we have two-phase algorithms, are going to do better than the eigenrep algorithm. Okay. But by only compute the compromised core general plus general only algorithm, then the detection rate may not be that good. But another observation is that the more sensors you have in the system, then intuitively you're going to achieve better detection rate because now you have more information to reason about. Okay. Now let's have a look at the detection rate, the false positive rate. Okay. For general only, obviously the false positive rate is 0 because we never make a wrong decision. We just compute the compromised core. Okay. And for the general plus MM, the two-phase algorithm, it's actually the detection rate, the false positive rate is always lower than eigenrep. Okay. So basically compare general plus MM and eigenrep, we see that we can have better detection rate and lower false positive rate. Okay. Okay. So another factor, which is accuracy of your estimation. Okay. We assume that in this experiment, we assume that there are always 20 nodes compromised in your system. But I changed my security estimation from 20 to 40. I mean, sometimes maybe I have a very tight estimation, but maybe my estimation is very loose. Okay. So we see that the first observation here is that for general plus MM, we actually achieve pretty high detection rate, no matter whether your detection, whether the security estimation is tight or not. Okay. But for the general only, that means only run the first phase, then when the security estimation is not good, then we may have very bad detection rate. In the worst case, we may not detect anything by using this loose estimation. Okay? So this also shows that what the maximum matching can give us. That means when we have 40, almost all those compromised nodes are detected by using the maximum matching using the second phase. Okay. And again, we observe that eigenrep cannot achieve high detection rate as high as the general plus MM algorithm. But one interesting observation here is that it seems as you increase the security estimation, the detection rate also actually increased. Okay. The reason is because now I include more and more nodes in my reported results in eigenrep. So by chance, I'm going to include more compromised nodes. Okay. But that is going to significantly increase the false positive you're going to introduce. So that's why we see that this is the detection rate of the eigenrep, the false positive rate of eigenrep is always higher than the general plus MM algorithm. And we see that the general plus MM algorithm's false positive rate is always bounded by 0.5. Okay, that's consistent with what we discussed before. Okay. So in conclusion, because sensor networks are subject to physical attacks, so compromised nodes may impose a severe threat to the security of sensor networks. So in this work, we propose a general framework to identify compromised nodes. We try to take advantage and model the uniqueness of sensor networks. Then we can propose optimal identification algorithm in the sense that we identify the largest number of compromised nodes without introducing any false positives. And we also discuss some techniques to further eliminate compromised nodes. Okay? And we use some experiments to evaluate our approach. Okay. So for future work, so far we are taking a centralized approach. That means everybody send an alert back to the base station. Okay. But this may cause high communication cost. But sometimes it may not, because sometimes the alert may just be inferred by looking at the information sent back by the sensors. They don't need to be explicitly sent to the base station. Okay. So another possible way is to use a decentralized approach. Basically, sensors looking around itself and reason which node are compromised. Okay. So this may give you a less communication cost, but because you don't have a global view of the network, your decision may not be that accurate. Okay? And again, we don't want to use a generalized decentralized approach for P2P systems. We still want to accommodate the uniqueness of sensor networks. Okay. And another direction is about sensor network reconfiguration. After you identify the compromised nodes, how are you going to deal with them? One natural choice is that I'm going to get rid of those nodes from my system. For example, I revoke all those keys of compromised nodes. But once you remove those compromised nodes, the functionality of the network may also be jeopardized. You want to cover the whole area, but after you remove those compromised nodes, this area is not covered anymore. Okay? So how I can efficiently and cost-effectively maintain the functionality and security of sensor networks? So this is actually a challenging issue, because you not only consider one operation, you want to consider the functionality of the network during its whole lifetime. Okay? So this is so when you make a decision, you want to think about what might happen in the future. So what is the best approach I can take to affect the future? Okay. Okay. So that concludes my talk. Thank you very much. Any questions? Yes, Mike.
So I just want to make a comment that the maximum matching approximation is in fact not an approximation in some situations. It's an exact solution. It's precisely when, and you can actually force that to happen. It's an exact solution to that is, the problem is no longer going to be complete if the graph has no odd length cycles. And you're in control, and you could perhaps make sure there are no odd length cycles.
I see.
By carefully planning the who checks who. So, for example, if you in one round you have the reds and the blues, and you can only check one of a different color, there can be no odd cycle.
Right.
And then you have an exact solution. So I think one of the reasons it's doing so well is it's not an approximation at all. It's actually finding, and in many situations, I don't know how many times it is happening.
Right. Actually, I tried both. We tried both max matching and vertex covering, but the result is always pretty much the same. Well, maximum matching is the best way to solve the covering problem. Yeah, this is the best approximation.
And it's an exact algorithm. So I'm not surprised that MM, I guess, is doing so well.
Okay. But if you only use MM, sometimes because the security estimation is not good, then you may just introduce false positives.
It deserves to do good, is what I'm saying.
Okay, thank you. Other questions? Yes.
Also, I had a common question. When you mentioned in the beginning that your graph consists only of the nodes of those integrities of concern, and I assume that implies there could be other nodes that are trusted. And I thought that if there are some nodes that are trusted at all times and they can also observe other nodes, then you can, if you include their information in the graph, the algorithm is going to be quite different and maybe more reliable.
Yes.
Because you get reliable input.
Yeah, that's a really important comment. So far we don't assume any. So whether we trust this node more than that one. So in practice, maybe you can assume that if a sensor is close to the base station, that base station can observe the behavior of that sensor. Then maybe I can have more trust on that sensor. So I should trust the information from that sensor more. So we haven't considered that scenario yet, but that's really a good comment. Yes?
So you mentioned in the beginning that the sensor networks are